So I'm going to talk about Lotka-Volterra systems and Darboux polynomials. So it started a while ago in 2014 in a paper with Theodoros, who was a postdoc at La Trobe, Quispel, Tron, Van Haken, and McLaren. They were all involved. Later, Ben Tapley got involved with the Darboux polynomials, and we got a better understanding of the things that we were doing back then. And Ian joined La Trobe recently, and we've been extending Lotka-Volterra systems, as you have heard in the talk by Victor today. So I'll start with a bit of background where I kind of encountered Lotka-Volterra systems. And then I will introduce the theory of Darboux polynomials, just define what it is and how useful it is to find integrals of Lotka-Volterra systems in particular, but the theory holds more generally. It's not confined to this setting. But I'll share with you some recent results where we have really, a very nice families of systems in this Lotka-Volterra class, and there's homogeneous ones, non-homogeneous ones, and Liouville integrable ones. So we'll see Poisson brackets. So thank you, Victor, for introducing those. That saves me a bit of time. And I'll share some new ideas on deforming Lotka-Volterra systems. And then they won't be Lotka-Volterra anymore. But okay, so I will tell you what a Lotka-Volterra system is later, although in the talk by Victor, he already told you where it is. But this is kind of the starting point. And I gave a talk on this before, and then everyone went like, oh, what is this? So now I have some simple examples of what this is. It's called a multisum of products. So each term is a product of the variables in a big sum. And if you look at, can you see my cursor? I think so. If you look at how the terms develop, so every function is homogeneous in the x's. And if you look at the indices, then they are written alternatively, or starting with an odd one, then an even one, and then an odd one. And that's the same here, odd, even, odd, and here as well, odd, even, odd. And if you just write down all possibilities of starting with an odd one, then an even one, and then an odd one, then you get these functions. So they are very well-defined functions. I mean, these functions arose from a study in actually lattice equations. So we had discrete partial differential equations where we looked at reductions. So in the same way that if you have a partial differential equation, you can do a traveling wave reduction so partial differential equation depends on, say, x and t, and then you can write the solution. You can propose that the solution only depends on a certain combination of x and t. For example, x minus ct. So c would be the speed of the wave. And if you make this ansatz, then the PDE reduces to an ODE. And that's called the traveling wave reduction. And then you can find traveling wave solutions by solving the ODE. And for a partial difference equation, so we have an equation that variable depends on two shifts, say a horizontal shift and a vertical shift. You can do the same thing. You can do a traveling wave reduction, and these are known as periodic reductions. So what you have, your equation is defined on a lattice. You can identify 2 points on the lattice and kind of roll up the lattice so you have a cylinder of lattice points. So then you get a periodic solution of your partial difference equation. And we were studying those equations. So starting from integrable lattice equations, you can look at these periodic reductions, and you can use kind of integrable structures for the partial difference equation to find integrals for the mapping. So the reduction becomes a mapping, and then this mapping, you can think about integrals. And we found that these integrals for a lot of the integrable lattice equations, we were able to write these integrals in terms of these functions. And then what we wanted to do was we wanted to, show that these maps that describe the periodic reduction, that they were integrable systems. So we would have enough integrals, but we also wanted to show that they were in involution. So to prove the involutivity of all these integrals for these maps, we studied these particular multisums of products, and we derived commutation relations for those. And then we used those commutation relations, so Poisson brackets I'm talking about. We use those to prove that the actual integrals for the reductions, that they were in involution. But then we had a thought, okay, well, we now know a lot about the brackets of these objects. Why don't we study these objects as integrable systems themselves? So that's when we wrote this paper, and that's where we found this Lotka-Volterra system that I will show you in a minute. Okay, so here's the definition. You've seen this definition before. If you have an n is 2r plus s dimensional Poisson manifold, what you want is s Casimirs and r integrals that are in involution. And if you can find that, then your system is Liouville integrable. So on this, the Poisson bracket on this space of functions in the x variables is a very simple bracket. It's a constant bracket, and it's given here. And with respect to that bracket, then these functions, if we just fix a to be 1 and b to be n, so we are on an n-dimensional space, then we just denote these functions by the subindex. They form an integrable system. So all these functions, they commute with each other if the index, the parity of the index is the same. And I forgot which one is the Casimir. I think Zn is the Casimir in the odd dimensional case. So then we have these nice Liouville integrable systems. So then one particular interesting system is the system connected to Z3. So that is the nice function of degree 3 that I explained you where these how these indices behave. And if you look at the Hamiltonian system, at this Hamiltonian system, then there is a subsystem that kind of decouples from the other equations. So all the odd variables, the evolution of these variables is expressed only in terms of the odd variables. So you can kind of forget about the even variables and just look at the odd variables. So if you do that substitution, you introduce new variables, you only look at the odd variables, then you get this Lotka-Volterra system. And it's a special case. I'll write down in a minute the general case of a Lotka-Volterra system, but this is what we found. But this system is not Hamiltonian with respect to the bracket that we had before, this kind of constant bracket, but with respect to another Poisson bracket, namely it is this bracket, which you have seen in the talk by Victor as well, it's usually called a log canonical bracket, because you can introduce kind of exponential variables and then it becomes a constant bracket. So, of course, if we swap I and j, with j bigger than I, you get the minus sign. And the Hamiltonian that gives rise to this special Lotka-Volterra system is just the sum of the variables. This is not a new system. We found that this system existed in the literature, in a paper by Bobby Jawlensky, but it's a special kind of reduction of that system. So this is also Liouville integrable, I mean, because we have all these integrals, and it is also super integrable. So it's a very special system with lots of structures. In fact, too many structures. So it's a too special case. But here's the general class. So we have an extra matrix A. So the matrix A that we have before is this would correspond. Oh, sorry, I can only write on this screen. So that special system is, of course, the matrix A that has zeros on the diagonal. We have -1 every entry on the lower diagonal and 1 here. So that is the special case. And in general, you can take basically any matrix A. Doesn't even have to be antisymmetric. You can add non-homogeneous terms. I call this the non-homogeneous term, the Ri. So the general Lotka-Volterra system in n dimensions has n squared parameters in the matrix A plus another n parameters in the vector R. So that's a lot of parameters. And in general, you would not be able to find any integrals in the general case. But the question here is now, for which values of these n squared plus n parameters do we have an integrable system? An integrable system can be defined in many, many ways. I mean, we've seen two definitions here: Liouville integrable, super integrable, but there's other notions as well. So we want to understand this class of systems a little bit better. Here's some details on the integrability of the special system that is taken from that paper out of 2014. We have these integrals. Here is basically a sum of the variables. I will later introduce some notation for that. This is just the sum of the variables. And here is an alternating product of the variables. And this is just one function times another function. And turns out that this function is an integral for that special LV system. This is for the case when n is odd, and we have a similar but slightly different expression when n is even. And then there's another set of integrals because we have an involution on the space. We can swap the variables x n plus 1 minus I with xi. We just swap them, and then we have we can insert that in the functions f. We get new functions g that are linearly functionally independent of the f's, but also integrals of the system. So then here is the kind of integrability result for that special LV system. We have that all the functions f commute with each other. Fm is the Hamiltonian, so the system is Liouville integrable. But it's Liouville integrable in two different ways, because all the functions g also commute. So that's another integrable system. And the system is also super integrable, or maximally super integrable. There are n minus 1 integrals by taking all these functions f and g together. they form a set of n-1 integrals. So there's a lot of integrability for this system here. Now, this system has been generalized in the literature, so you can scale all the variables xi by just a constant, that's just a scaling. But of course, once you've scaled it, you can investigate studies where some of the AIs are zero, and then the integrals that you had no longer exist, and you have to find other integrals. So that's one game that they played, and they found basically the same result, that all these kind of special subcases are also Liouville and superintegrable. And then they looked at those sets of integrals, and they said, well, maybe we can add non-homogeneous term. So basically they thought about, here are the integrals, what non-homogeneous terms can I add? And turned out that you can actually add some non-homogeneous terms while preserving the same set of integrals. Of course, this doesn't answer the full question that, all right, well, I mean, you don't need to have the same set of integrals. You could have another set of integrals that also gives you integrability. So it's just a partial question of, but it gives a generalization of the system. All right. Few years ago, not too many, we showed actually that for any ODE, so this is not a result on Lotka-Volterra systems, that any ODE can be modified by adding some kind of non-homogeneous term. You can add a constant function times the vector x to any ODE, and then you preserve the homogeneous Darboux polynomials. I am going to explain you what these Darboux polynomials are, but just mentioning now that immediately this leads to the fact that you can always add this kind of non-homogeneous term to this Lotka-Volterra system and still having it superintegrable as well as Liouville integrable. Other systems, most people study kind of small dimensional Lotka-Volterra system, so 2 components. That was the original one. That's kind of fully solved, and everything's known. For 3-component systems, there is already a lot of different cases where you have different kinds of integrability, different solution methods, different relations to Prem-Lefebvre equations, and all kinds of things. And that's only 3-component Lotka-Volterra systems. So also in this paper by Meyer, he constructed lots of general solutions, but all in the class of 3-dimensional or 3-component Lotka-Volterra systems. Now, quite recently, these people from Germany studied an n-component Lotka-Volterra system, and this has one parameter in it. There's the parameter k in it. They discussed integrals, integrability. Also, they studied discretization. We have worked on discretization of some of these Lotka-Volterra systems that I am discussing today, but I won't go into any details on the discretization. Okay, so here is the theory of Darboux polynomials. A Darboux polynomial is just a polynomial, or even you can extend it to a function. But let's talk about polynomials. A polynomial such that if you take the time derivative, you get back the polynomial with some kind of factor in front of it. And this factor in front is called the cofactor of P. So it's a very simple, innocent definition. And then you can you have the following result. Why is this a nice thing? Well, if you take a product of Darboux polynomials, or even a product of Darboux polynomials with powers, then you will get another Darboux polynomial. So this whole sum, this whole product is itself a Darboux polynomial. And then you can ask, well, what is the cofactor? The only thing you need to know is the Leibniz rule to derive that the cofactor of that Darboux polynomial, this thing is the same as this thing, and the cofactor is just a linear combination of the cofactors of the original Darboux polynomial. So that is nice. And I mean, there is one particular Darboux polynomial which is kind of more famous than the others because it's an integral. So a Darboux polynomial with cofactor 0, we don't call that a Darboux polynomial with cofactor 0, but we just say it's an integral. So it's preserved by the evolution of the system. And because of that, if you have enough kind of Darboux polynomials and the cofactors, they form a linear space, let's say, for these Lotka-Volterra systems, all the cofactors are just linear functions of x, of the xi's. If you have enough of them, then at some point, they can't be independent anymore. So we have relations between the cofactors, and these relations, we can use them to create these integrals. So as soon as you have a relation of this form between the cofactors, you can just take these coefficients, plug them into the exponents of your Darboux polynomials, and you see that you found an integral. So that is very nice. Here's another notion. Not going to go too much into this, but we say that ODE is measure preserving if there is such a thing, a measure. And this function in here, it's the reciprocal density of the measure. That thing is a Darboux polynomial with cofactor equal to the divergence of the function. Just one sec. Sorry, I'm in a Zoom tour. Okay. So I'm giving a presentation. Sorry. Yeah, okay, thanks. Yeah. Sorry, guys, that was my host going to lunch. I will have lunch a little bit later. So this is the definition of measure preservation, and the density, the reciprocal density, is a Darboux polynomial with cofactor equal to the divergence. So you can just calculate the divergence and then, do a similar thing as with the integrals. You just have to solve a linear equation if all your cofactors are linear expressions, and you can find your density. And then here we have another notion of integrability that I just want to throw in. So this is very similar to superintegrability. For superintegrability, you need n-1 integrals. But if you only have n-2 integrals, then Arnold is saying, well, that's not a problem. That's fine as long as your map is measure preserving. And this type of integrability is called non-holonomically integrability. So we can also, when we are studying these Lotka-Volterra systems, we're looking for integrals. If we have n-1, then we say, okay, hooray, we have maximal integrability. If we only have n-2, then we have to check measure preservation. We can think about Hamiltonian systems, Liouville integrability, and all of that. So this is another option. Okay. Now, because of all these nice integrals for these systems, we had these f's and g's, but they are basically derived functions from more basic functions, as I kind of alluded to. We have sums of variables, of subsequent variables. So we go from I to I plus 1, all the way up to xj, not skipping a single variable, and that is a function pij. And then we have these alternating products of variables, and we call them qij. So all the integrals of all the known kind of integrable Lotka-Volterra systems that were studied by us and by others in the literature can be expressed in terms of these functions. And the C's, we just use them to express the Poisson brackets. So with respect to this bracket, we know exactly how these functions Poisson, the brackets between these functions, and they form a quadratic algebra. So if you look at the definition of C KL, then either K is equivalent to L mod 2 or not. And in the first case, if it's not equivalent, then we just get a single PKL here. If K is equivalent to L, then we get the difference of two P functions here. So this is a quadratic function. This is a P and that is a Q, or a difference of P's and a Q. And here we have two Q's. You can actually show that this whole sum is either 1, 0, or -1. So that's a nice Poisson algebra on these functions. And we can use this algebra to study the involutivity of all expressions expressed in terms of these functions. And we can look how this Lotka-Volterra system arises, because now H can be written as this function. And of course, the variables can be written in terms of the capital P's in this way. And then from these relations, we see that the bracket of the variable xk with H really is equal to this thing. So this is another way of writing the special Lotka-Volterra system. And now you can see that all the P's functions, the bracket with the Hamiltonian produces a P function. So the P function is a Darboux polynomial, and this is the cofactor. And similarly, the Q function, if you take the bracket with H, you again find this function either here or here, depending on the parity of L and K. But in the first case, this is the cofactor. In the second case, that is the cofactor. But now we observe that this cofactor is the same as that cofactor up to a minus sign. So if we take the product of PKL and QKL, when L is equivalent to K mod 2, then these cofactors, they just cancel each other in an additive way. And we get 0 as a cofactor for the product of P and Q. So the product of P and Q is really a function. And these are very nice functions. They actually are much nicer functions than the F's and G's we had before, because they are local. So they only depend on the variables K up till L, and not on all too many Darboux polynomials. There is n times n minus 1 over 2 Darboux polynomials, and way too many integrals. The number of integrals, I can't see it on my screen because there is a little box with screen sharing in front of it, but it's basically a second degree polynomial. So the number of integrals goes with n squared, whereas of course there can only be n minus 1 independent integrals. So too many integrals, so the system is too special. We can have other systems with more parameters that have less structures but may still be integrable. Okay, so for the rest of the talk, I'm going to tell you, this is a bit of an overview on what the rest of the talk will be. So we're going to study this special A matrix that I wrote down on the slide before, but now we're going to add this non-homogeneous term in a 3-block form. So that means that we have a vector of constants, and the first k components of that vector, we use the same constant, then the next L components of the vector, another constant, and the last m components of the vector, we have the third constant, and these constants are related. So we have that the middle one is the sum of the other two. Then we study this case. So there's heaps of different options now. Just adding these terms, we kind of sometimes destroy the Hamiltonian structure. We sometimes don't have enough integrals to be super integrable. So it suddenly becomes a very wild zoo of different systems, different cases. And I'll tell you a little bit more on the details later in part 1 of this talk. This is a very long introduction to the talk. All right, the second thing is we looked at completely general A matrix, so n squared. So this matrix has no parameters in it, the special matrix. But now we look at a completely general matrix with n squared parameters. And then by imposing that certain functions should be Darboux polynomials, we're going to impose conditions on all these parameters. And we will find cases where we have enough Darboux polynomials and the Darboux polynomials generate enough integrals for the system to be super integrable. So that will be the second part of this talk. And that can be generalized from small Darboux polynomials to bigger Darboux polynomials. And then we can study a similar thing. But so whereas here we want kind of enough dp's to generate enough integrals to be super integrable. In the third part, we will just start with not the general matrix, but an antisymmetric matrix. And if that's the case, then the Lotka-Volterra system is automatically a Hamiltonian system. And then we want to find integrals that commute with each other. So we don't need as many integrals, but we want them to commute. So we get different conditions on the matrix A in that case. And then lastly, if time permits, I will tell you a little bit about using Poisson subalgebras and commutants to deform this special LV system that we had saw before. All right, so that's the plan. And let's start with part 1, the special A matrix. So the antisymmetric with ones on the top right and minus ones on the top left, and this block system of non-homogeneous terms. So it depends on whether the blocks are odd or even. And then we get lots of different cases. So I won't go into too many detail, but there are 5 different cases which are odd. So even stands for, odd, even. The E stands for even, of course, and the O stands for odd. We have 5 different even systems, 3 different odd systems, and then there's some other ones, the N and the M systems. The E and the O cases are all Hamiltonian systems. We can write down Hamiltonians in terms of these functions P and Q that I introduced, and that's all very nice. And then the systems N and M are not Hamiltonian. Then here, what we can do, because of this theorem that you can always add a constant, well, you can add a constant here, but if the constants you can only do that within each block. So in the first block, you can add this constant b, but then integrals that, or Darboux polynomials that only depend on the variables inside that first block, they are preserved. As soon as a Darboux polynomial extends over 2 or 3 blocks, then those are not preserved. So we are going to use these nice integrals that are the product of a p and a q. They are called these i's. So I, say KL is just PKL times QKL. And if the K and the L are inside one block, then that is still an integral for the entire system. So we can look at how many are there of these kind of integrals. And then depending on whether your K or L is even or odd, you have one more or one less. And here is the result. So for the the first even system, we have n over 2 minus 1 of these integrals. These integrals all commute with each other, and we have an Hamiltonian. So we have a Liouville integrable system. That is all nice. For E2, 3, and 4, these integrals are not enough. We are missing one integral. So we have to work harder to find that integral. And I'll show you in a minute what it is. For E5, we're missing 2 integrals. Here we have exactly the right number of integrals because we can add the Hamiltonian and we have a Casimir. So then we are right. In this case, we're missing 1 integrals. And the integrals that are not of this form, they are integrals that are kind of not local. They're not confined to one of these blocks. They depend on all of the variables that we have. And you can basically find these integrals by doing, well, in finite dimensions, you can do that. To do it in arbitrary dimensions, which is what we do, you have to just do it in enough dimensions so you know what there is, and then you can use general results to prove this. But to find it in low dimensions, what you have to do is you have to just calculate the cofactors and solve a linear problem. Namely, you look at the cofactors, you write down your system, you want their relations between these systems. And there's one thing that I forgot to tell you. Let's go back to a very important thing. What is nice about it's my Lotka-Volterra system. Here it is. So what is nice about this system, it already has n Darboux polynomials. So this function xi, if you differentiate it, we get xi times some other thing. So this thing here is really the cofactor of xi, and xi is a Darboux polynomial. Now this is an n-dimensional system, so we already have n Darboux polynomials. So if you have one more Darboux polynomial, since all the cofactors, this is a linear combination of the xi, let's say Ri is 0, then the space really is an n-dimensional space. So if you have one more Darboux polynomial than the n you already have, you have n plus 1 Darboux polynomials, hence you have n plus 1 cofactors, linear functions, and they can't be independent. So one extra Darboux polynomial gives rise to an integral. So that is really the nice thing here. And if you have something that is not homogeneous, you actually need one extra. You need 2 Darboux polynomials to find an integral. Okay, so this is how you can kind of find all these integrals. You take the cofactors, but you also take the cofactors of just the coordinates, and then you solve a big linear system to find these. And once you know what there is, you can use the Poisson algebra for these functions P and Q to prove that really this is an integral. For E3 and 4, we have these integrals. For E5, we needed 2 more, and we have found them. So that is all good. For O1, the odd systems, there is a Casimir. For O3, we have 1 extra integral, which we needed. It commutes with all the other ones in this set. Okay, so that settles the Liouville integral cases in this class. And then you can think about, okay, well, what about more integrals? And then there are cases that have n-1 integrals. There are cases that have n-2 integrals. There are cases with n-3 integrals. All these cases, apart from this one, are also Liouville integrable. But here is the n1 is, the n is from non-holonomically integrable. So it's not Liouville integrable, but it is non-holonomically integrable. And then there is this interesting class where we don't know anything about the integrability, but we do have n-3 integrals. On the other hand, we have a theorem that each of these 3-block systems can be kind of contracted down. If you take the right Darboux polynomials and you write down the system satisfied by these Darboux polynomials, you can contract it down to one of these systems. These systems can be solved. It's kind of a formal solution, but you can check that this is a solution of the system. And then you can do a change of variables such that your big LV system basically, it not really decouples, but almost decouples. No, it does decouple. This one is a separation of variables. And then given the solutions of one of these 2 or 3D systems, you can solve it completely. And then there is the question, okay, well, we had this system M1 where we don't have enough integrals to be kind of formally integrable, but we can solve it. So is that an integrable system or not? I mean, what are the properties? And are there maybe hidden integrals that we don't find? And this is the simplest kind of case. So maybe a nice toy model to study a little bit further. Okay, this is a second topic. I don't think I'm going to go through all 4 topics, but what we do here is starting with a general A matrix, and we say we want this thing to be a Darboux polynomial. What is the constraint on the matrix such that that is the case? And then well, first of all, we need these constants to be the same. The constants in front of the equation for xi and the equation for xk, they need to be the same. Now, this is not really a condition on the matrix. This is a condition on the coefficients here. So once you have the right matrix, you can just read off what is the alpha and the beta. We have either, this is a special case of the matrix. So this is a very constrained case where you just have lots of zeros. So if you don't have the zeros, then this is the main condition. That the row, if we look at this condition, then the rows, the ith row and the kth row, this is I here and this is k here, of the matrix A are basically the same apart from column I and column K. And in all other columns than I and K, the rows are the same. So that is a nice constraint on the matrix A. And then the question is, okay, well, we can then construct a matrix that has one Darboux polynomial. We can then use that Darboux polynomial and all the other Darboux polynomials we already had, the coordinates, to find an integral, all very nice. But how many of these constraints can we impose on the matrix A? Can we indeed impose n-1 constraints and still have kind of parameters? And the answer is yes. You can associate this dp to the edge of a tree. So if you think of a tree on n vertices, then each vertex connects to one of the variables. The ith vertex, let's label it xi, and then an edge between vertex I and vertex j would correspond to a Darboux polynomial of this form. And if you do that, then you can see that you get in the matrix, you can solve the matrix, all the constraints. You still have 3n-2 parameters in your matrix left. And you can then prove in the end that all these integrals that you get from these n-1 Darboux polynomials are all independent. You have a super integrable system with enough integrals. So I'm not going to show you how to construct this A matrix, so I skip this part. And yeah, maybe one point on this system that you get. You can write the system in reduced variables. So if you take, instead of the variables xi and xj, if there is an edge between them, you can look at the ratio of the two variables. And in those edge variables, the system reduces by one dimension. You still have the n-2 local integrals. And that system kind of decouples. It's not of LV type, Lotka-Volterra type, but the structure of the tree behind the system tells you exactly how to solve which equation to solve first. And then depending, in this case, you can see that you can solve y1, y2, y3, y4 first. They are decoupled. And then based on the solution of these equations, you can solve the other equations. So then these three systems, the reduced three systems, can be solved exactly. And this is the solution for the example. Okay, so now this can be generalized to, instead of looking at 2 dp's, you can look at MDP. So instead of just a linear combination of 2 variables, you have a linear combination of m variables. You can write down the condition on the matrix A. And here it is. This is the condition. And this is basically how you can solve this condition. So you can write down the solution for the parameters, and there is an expression for the solution to this system for the matrices. It's a choice of parameters in your matrix. And then you can ask, all right, well, now instead of edges, we have hyper edges because we have more vertices connected by the edge than 2. And you can think of all possible hypergraphs, whether they connect to the dp's of an LV system. And we kind of say that if particular hypergraph is the realization of the DPs of an LV system, then we call it LV admissible. And then there is a very interesting question that what we know is that if you do a linear transformation, then these Darboux polynomials are preserved. So you can take a system, LV system with one particular hypergraph, and you can introduce new variables that are Darboux polynomials. If you write your system in terms of a different set of Darboux polynomials, then what you will find is another LV system. But this LV system will have exactly the same number of Darboux polynomials, but it may be connected to another hypergraph, which is not isomorphic to the hypergraph that you started with. And then you would say that these non-isomorphic hypergraphs are still LV equivalent because there's a linear transformation between them. So you can study the equivalence relation on the set of admissible hypergraphs, and that is an interesting thing to do. So it's a hard problem. I've solved it for dimensions up to 5, and I found a nice new integrable system at that order. So this is for all the possible non-isomorphic hypergraphs of order 3. You can show that these are LV equivalent. So the system with a 2dp is really, by a linear transformation, equivalent to the system with 3dp. And this is a system with two 2dps, and it is equivalent to a system with one 2dp and one 3dp. These systems with three 2dps, that's equivalent to this system with two 2dps and one 3dp. Of course, these three 2dps don't give rise to three independent integrals, because we are in dimension 3 and we can only have two of them. So they give rise to dependent integrals. And this is a special case. Okay, let me go through the interesting case where we have 5 hypergraphs of order 5 with 4 hyper edges. So what I've done here is I've just, because there's too many non-isomorphic hypergraphs, I've just put down one representative of the equivalence class, and I've done the one with where the hyper edges have lowest degree. So here you can see this is actually a tree system. There is another hypergraph that is not a tree system, but it's LV equivalent. It's in the same class. So we consider that to be a tree system. This is also a tree system. That is a tree system. There's 12 other hypergraphs that are not trees, but they're all LV equivalent to this one. Now, this is not, this is also a tree system. It's not so interesting because we have this loop here. So the integrals, there's not 4 independent integrals for this case. This also doesn't have 4 independent integrals. This also doesn't have 4 independent integrals. But this one has 4 independent integrals connected to each of these Darboux polynomials. This is a 2dp, another 2dp, another 2dp, and a 3dp. And it's not equivalent to one of these tree systems of order 5. So this is kind of a new system. And surprisingly, I mean, I say surprisingly because I don't understand why, but it has exactly the same amount of parameters as the tree systems. So that is something still to understand. Here is the matrix of this system, and I'm just going to finish with a conjecture and then skip the other parts of this talk. What I have been looking at, so this is how far I could go, because the number of hypergraphs is really immensely big. So on a computer, This is kind of roughly where you can go, maybe order 6 on a supercomputer. I haven't used a supercomputer, I've just used my laptop, so that would be possible. But what I've been able to do is looking at 3 systems and look at the number of the equivalence class in the set of hypergraph systems that are equivalent to these 3 systems. And what I found was that each tree is in a different equivalence class. So the statement is that non-isomorphic trees are not LV equivalent, and I've been able to check that for order, well, we've seen it for order 3, 4, and 5, but I've specifically been able to check this for order 6, for order 7, and for order 8. So, I mean, there are 126 hypergraph configurations that are LV equivalent to this particular tree. But the important thing is that each tree gives rise to a different equivalence class of hypergraphs. I think I will end here because then we still have 2 minutes for questions.